This video covers Part 2 of Section 1.1, Statements and Logical Connectives. We can summarize the definitions of the 5 logical connectives by listing their truth tables. A truth table for a statement form contains a column for each component statement variable and a column for the statement form itself, along with a row for every possible combination of truth values of the statement variables. The truth tables for the 5 logical connectives are as shown. So for the negation, there's exactly one statement variable p, and so there's a row for each of its possible truth values. When p is true, the negation not p is false. When p is false, the negation not p is true. For the conjunction, there are 2 statement variables, p and q, and so we have a row for each possible combination of truth values for p and q. So p and q can both be true, or p could be true and q false, p could be false, q true, and p and q could both be false. And then we have the corresponding truth values for each of those combinations. And similarly for the other 3 logical connectives. Note that for a compound statement form containing 2 statement variables p and q, there are 2 choices of truth values for p and 2 choices for q, resulting in 2 squared or 4 combinations of truth values for p and q, and hence 4 rows in the truth table for the compound statement form. For a compound statement form containing 3 statement variables p, q, and r, there are 2 choices of truth values for each of the 3 variables, resulting in 2 cubed or 8 combinations of truth values altogether, and hence 8 rows in the truth table for the compound statement form. In general, there will be 2 to the k combinations of truth values for k statement variables, so the truth table for a compound statement form containing k statement variables will have 2 to the k rows. We can construct truth tables for more complicated statement forms as well, as in the following example. So in this example, we want to construct the truth tables for the following statement forms. And first we have p or q implies p. This statement form contains 2 statement variables, p and q, so the truth table will contain 4 rows. We need to include columns containing the truth values for p, q, and the complete statement form p or q implies p. We also include a column containing the truth values for p or q to help us compute the truth values for the complete statement form. So the table will contain columns as shown. Start by filling in the columns for p and for q. It's important to write the rows in the same order as shown here. We can then fill in the table a column at a time. So here we have the truth values for p or q, and then the truth values for the complete statement form p or q implies p. For part B, we have p or q quantity and not p and q quantity. This is the statement form for an exclusive OR. This statement form contains 2 statement variables, p and q again, so the truth table will contain 4 rows. To assist in computing the truth values for the complete statement form, we include columns containing the truth values for p or q, p and q, and not p and q. The resulting truth table looks like this, and we can fill in the columns one at a time. Resulting in this truth table. This statement form is true when either p is true or q is true, but not both, which corresponds to an exclusive OR. For part C, we have the statement form p and q implies not r. This statement form contains 3 statement variables, p, q, and r, so the truth table will contain 8 rows. It's again important to write the rows in the same order as shown here. If you think of true as being a 1 and false as being a 0, then starting at the bottom and reading up, the rows correspond to the numbers from 0 to 7 written in binary. So our bottom row is false, 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 which is 0, 0, 0, or just 0 written in binary. The next row up is false, false, true, which is 0, 0, 1, which is 1 written in binary. The next row up is false, true, false, which is 0, 1, 0, which corresponds to 2 written in binary, and so on. We then fill in the truth table one column at a time, as usual. And there's our resulting truth table. As given in its definition, the conditional statement, if P then Q, is defined to be false when P is true and Q is false, but is true in all other cases. There are various ways this choice of truth values can be justified. Consider the following example. Suppose your boss makes you the following promise. If you work hard, then you will receive a raise. Under what circumstances are you justified in saying that your boss spoke falsely? That is, under what circumstances is the above statement false? The only conditions under which you can rightly conclude the statement is false are that you did work hard, but you did not receive a raise. In other words, the hypothesis is true, but the conclusion is false. Your boss's promise only says that you will receive a raise if a certain condition, your working hard, is met. It says nothing about what will happen if the condition is not met. If we wish to consider such a sentence a statement, it must have a definite truth value for all possible truth values of the hypothesis and conclusion. So it makes sense to consider such a statement to be true, except when the hypothesis is true and the conclusion is false. There are other, more mathematical arguments to justify the choice of truth values in the conditional statement. These will be discussed in a later section. A conditional statement that is true by virtue of the fact that its hypothesis is false is said to be vacuously true. This fact is the basis for a type of mathematical proof, a vacuous proof. Next, we want to look at tautologies and contradictions. In a previous example, we saw that the compound statement form P and Q implies not R was true for certain values of the statement variables P, Q, and R, and false for others. Such a statement form is called a contingency. On the other hand, some statement forms always have the same truth value, either true or false, for all values of their statement variables. As we'll see later, such statements play an important role in mathematical proof. So we define a statement form that is true for all possible choices of truth values of its statement variables to be a tautology. A statement form that is false for all possible choices of truth values of its statement variables is called a contradiction. As mentioned earlier, a statement form that is neither a tautology nor a contradiction, so is sometimes true and sometimes false, is called a contingency. For our next example, we want to show that the statement form P and P implies Q, quantity implies Q, is a tautology. To show the statement form is a tautology, we need to show that it is true for all possible truth values of its statement variables P and Q. The most straightforward way to demonstrate this is to construct the truth table for the statement form. So we'll start with our truth table set up as shown, and fill in the truth table a column at a time. And since this is true for all choices of truth values of P and Q, we see that the statement form is a tautology. For an alternative approach that doesn't involve constructing the truth table, note that the only way the statement form can be false is when the hypothesis, P and P implies Q, is true, and the conclusion, Q, is false. In order for the hypothesis, P and P implies Q, to be true, we need both P to be true and P implies Q to be true. But P equal true and Q equal false imply P implies Q to be false. Since P implies Q cannot be both true and false, it's not possible for the statement form to be false. It must then be true for all choices of truth values of P and Q, and hence is a tautology. Many of the statement forms which are tautologies occur frequently enough in logic that they've been given special names. This particular tautology, P and P implies Q, is called modus ponens, which is Latin for method of affirming. For the next example, we want to show that the statement form R and not R is a contradiction. To show this as a contradiction, we need to show that it is false for all choices of truth values of its single statement variable R. Okay, we can see this from the truth table. Since R and not R is false for all choices of truth values of R, then it's a contradiction.